What can we do to speed up a program? Interactive. Do we have some ideas? Can someone tell me a way of getting a program that exists to run faster? What can we do?
Remove the bloater code.
Yes, so we are improving the program, right? We're doing it better. Yes, very good idea. Do we have another idea?
Move operations to the parts of the program and in which they will be executed faster and more effectively.
Yes, okay, yeah. So again, changing kind of the logic, but making the program better and more effective at what it's doing, yes?
I mean, maybe traditional, but make as least calls as possible to networks or databases, just holding cache as much as possible.
Absolutely, yes. Again, it's about improving the code, you could say. Can we do something else than improving the code, by the way?
Reduce operations and loops.
Yes, improving the code.
We can put it on the better machine.
Yes, better hardware, of course. That's the first thing you can think about. And some of the people are actually reaching there first. Anything else? I was thinking about
Data structures.
improving the code.
Yeah.
Yeah, okay. I won't hold you on this one. So when I was thinking about this, of course, you can buy better networks or better hardware. But you can change the programming language as well, right? Potentially. We won't do this here, so you don't have to worry. But you can actually run, in some cases, programming languages that are better optimized for whatever you are doing. And the last one is, the way I chose to word it, but this is basically what many of you told already. Rewrite the program to do the same with less work or in a better way. And the purpose of this talk is, of course, to focus here. You can buy another computer at some other time. Yes, so optimization. So what I want to sell you here is a way of thinking. Usually I don't introduce myself so very much on this. I don't think I ever actually did this on the meetups before. But anyways, I've been working more than 30 years professionally in technology, in IT. And now I'm serving as an enterprise architect in a major corporation. So what I'm trying to do with this talk, actually, not for bragging, just I want to, if I can, give you a little bit of the mind tools or the way I think when I'm starting to optimize something. So that's what I'm trying to do with this talk. And actually, I just give it and see, because probably it will be some variation of this that might be helpful for someone, I hope. Hopefully for many. Anyways, of course, we will do some practices just to see if whatever I'm saying is just talk or if it's actually making some improvement. So way of thinking. One thing that I want to say, though, this talk, as you can see here, won't be that much about recipes. Okay, you can find lots of YouTube videos or Stack Overflow answers that are more like, okay, this is a recipe. Okay, you have a Node.js program, then you can run the PM2 program manager. You can, if you have several promises going, then you can make them run at the same time and so on. You know, these are more very practical things that you can just apply. This talk is more about engaging us so that we can have a tool of thinking more, so we can, yeah?
It's more about why and not only necessarily what, right?
Exactly, so that you can do your own recipe, right? You can think about something, and in your program, you can optimize your program according to the findings that you come to, hopefully. Yeah, exactly. So not the monkey coder, but a good coder, hopefully. Don't optimize. Very strange to have this slide on the beginning of this talk, but this is also a very, very important point. I'm sure that you know there is actually almost like a sickness in programming that is called premature optimization. That is like you are still writing. You haven't even released version yet, 1. Yeah. I could make this run faster. And you don't even know why. You haven't even measured where you are and such. Don't do that, right? Also, I wrote the skill trap. The skill trap is that first you are a junior, so you are kind of happy and you're coding and you just get the program to work. But then when you get better, you are starting to see the possibilities of optimization. And then it starts to be like when you're working somewhere, you want to share this. You know, you want to give the value for the employer, or if you're working on your own project, you want to do it as good as possible. But that's the skill trap. Optimize. Okay, let's see when we should. Sorry?
It's a bottomless pit.
Exactly. You can do it as without any limit. So when do we optimize then? I was thinking about this, and the general rule that I'm trying to go for is only when it's the best thing we can do right now. So if you're working in a company, then your boss will probably tell you that, okay, is this the best business value you can create right now, right? A business value would be, for instance, if the program is so slow, so lacking, you're pressing a button and it takes like 20 minutes before the report is printed, and during the time the program is frozen, then probably this program has a problem with the usability, and that might be the most important part to do right now. Then you have the issue when you have infrastructure. If you have 20 servers, then if you could run twice as much users on those 20 servers, that would be good, and as a hobby. And I wouldn't underestimate this one. I love optimization, as you might see on my style of talking. I actually love this subject. So as a hobby, this is like you can play chess, you can solve crosswords, or you can do optimizing just because it's fun and see how fast something can get in some cases. And this is very good, of course, to just keep the brain going. So you can do that. This is easily worth it. Very important point here is to measure. If you don't have a baseline, then it's completely useless. If you just say, oh, it feels better now. Yeah. If I puff my pillow, it feels better now. It doesn't mean anything. This is not something that's scientific, right? Scientific is when we measured, and we know that it's better. One thing to note here is that it's called profile, and this is this fancy IT word. You run a profiler. This is not part of this talk, but you can find those tools. They're called profilers, and you can find it basically for any language. What this tool will help you with is do all the timings, and you will know where the program is spending its time. Not necessarily why, but it's good to know. So the way of thinking, and I would say that this is the most important question that is kind of going in the background of me when I'm optimizing all the time. What am I asking the computer to do? And of course, on the program level, it might be a little bit abstract because usually the program is more than trivial, right? But once you come to the function, it's a little bit more interesting. What am I actually asking the computer to do here? Is it like heavy, or is it like lightweight? Will this run fast? And of course, in the statement, even more interesting. When you are writing a complex statement, then think about what those operations mean, especially if you have like calls to something. It might actually be very heavy. So to start delving at what we can do with the program, we have to find some kind of generic pattern to go for. And the generic pattern I usually go for is the diagram of every program. Every program basically is input, processing, and output in some way. Now you can say, okay, yeah, but when I'm starting Word, it's not that I'm loading a file, Word starts up, closes down, and another file comes out. So it's not the truth in this case. But what I mean is like this. If you have Photoshop, for instance, then it's a collection of like thousands of small functions or programs, you could say. For instance, resize image. So what is the input, processing, and output here? The input is the original image at a certain size, and also what you choose should be the final size, right? And then the processing, and then you get some image out. So, and you will see that this is true when you break down basically any function in the program. In online banking, as another example, you have online banking and you are doing the bank statement. You want to know what happened on my account during the last month. So you are pressing, download PDF, right? You're choosing February and print PDF or download PDF or whatever. What is happening? So the input data is the bank knows it's you. It knows which month you chose. And there is the transactional databases inside the bank that it keeps track of what is happening to all this money. And together the processing and some work, and then you get download the PDF. Another example is zip. Why am I choosing to do the example zip after the other ones? Because this should be a much simpler example. It's much easier to understand, right? You're just zipping something. So let me ask you this question. If you have sitting at a computer that has 4 gigabytes of RAM, and you have a file on this computer that is 5 gigabytes big, can you zip it on this computer?
No. Yes.
Yes. No? No. Yes.
It was
Yes.
working
Yes.
some RAM,
The answer is yes.
Storage.
Yeah.
The storage.
Exactly. So, and here's the thing. I just wanted to show you, just to understand that it's not just 1, 2, 3 here. What is actually happening with zip is that it's actually taking this input file that you want to zip, or the whole folder or whatever, and it just takes this like imagine a big loaf, right? And it starts to chopping it. And each of those small bread pieces becomes this package. Okay, now I'm using several metaphors, but anyways, you understand what I mean, right? It's cutting it up in those small packages, and then the processing is actually happening on each of those packages, which means that the zip can happily run together with your game and with other things that are happening on the computer. It just uses as much memory as needed for those packages. So this is called, the concept is data streaming. The important part to understand in optimization here is that all those things can happen all the time, right? And just going all around until all the data that came as an input is finished. It's just streaming through. So the speed of the program is, of course, the total time. And that's why it's so important to measure, because you need to get the feeling of what is happening and why is where is actually the time spent here. So yeah, this is basically addition, right? But measuring is to see which part is actually taking time. To do something about it, it's very, very good if we know a little bit about the computers we're working with. So probably of you, you all know this, because even if you just went and bought a computer once in your life, you read numbers about this, so you will know about those parts. I chose those parts that are very, very easy to understand. The CPU, so CPU is actually stands for Central Processing Unit. So it's a processing, right? We understand that the wheel there that was doing all the stuff is happening in the CPU. Basically everywhere. We can say this, at least for the easiness of this talk. Some things are happening somewhere else in other cases, but anyways, in this talk, every processing is happening in the CPU. Then we have the RAM. So in the CPU, there is some memory. It's called cache memory. We won't go in so much into that, but we will actually use cache memory in one of example very soon, and we will see if it matters. Cache memory in computers is between like, let's say 4 megabytes and 16 megabytes, I would say. This is the normal sizes. Then you have, of course, fringe computer servers and such that might have more or less. Memory in a computer today is, let's say, yeah, around 1,000 times more, right? Like 4 gigabytes to 16 gigabytes. This is a normal memory today. Then we have the SSD, which is mass storage. The size doesn't matter that much, but usually between like 240 and let's say 2000, which means 2 terabytes. This is the normal sizes. And then we have, what is this? Ethernet, a network connection. Of course, we cannot say how big is the network connection, but we can say how fast is it. So these are the things that we can work with when we are optimizing. So another fancy word in computing is latency. And latency is sometimes a misunderstood word, actually. Anyway, so the definition I will propose here is the amount of waiting time for something to finish. This is actually a word that is used in English for other things as well. For instance, when you are getting sick, then the latency is from you get the virus until you get sick, you know. Anyways, so latency is until it's finished. In computers, it's usually like you have to seek something up and then load it. Or if you are storing something, it's going the other way around. So then you are actually pushing out something, and you also have a transfer. So that's the latency. Latency, ping. You probably all know ping, right? So latency and ping, and this is the misunderstanding, by the way. That's why I'm doing this picture. Many people are like playing an online game or something, and then they have latency and ping is usually used almost interchangeably. But that's just because in ping, the latency is almost like the ping. So that means that in the special case of ping, it's latency, you could say. So I was thinking about if we could do a small like exercise here together so that we understand what latency is. The exercise is extremely easy. I will say hello, and you will wait until you hear me say hello to the end, and then you will answer me with hi there. Okay? It's so easy, and we can all do it. Are you ready? I will count down from 3. I would think that a room of programmers would be able to do this. Yes. So 3, 2, 1. Hello.
Hi there.
Yeah. The latency is from when I started to say hello until I heard the end of there when you said it. Then this is ping.
So it was the time of you saying it. It was
You
then
start to say
the
Yeah.
the distance, the time that it used to reach our ears.
Mhm.
Then the time that we processed that it actually happened.
Yeah.
Then the time that we actually started and finished our sentence, and the time it reached your ears.
And until I heard it, yes.
Yes.
Yes, that's latency. So now we understand this thing. And to better understand it, even better understand it, is if we are doing a download from a file server in New York, then the latency is, and this is actually one of the very cool things about our world, that our world is so small that speed of light is not enough, I would say. Because what happens here is that I'm clicking on this link, right? Or you are doing, or you clicking on this link. So it takes 50 milliseconds until this click kind of lands on this server. And then this server starts for a few milliseconds to think about what it should do and find the file and such. And then it starts streaming back to you this 2 gigabyte file. And then it's streaming. Actually like this. It starts streaming. Again, it takes 50 milliseconds after it started streaming the first byte until you see the first byte. Then let's say, okay, streaming. At some point, this is sending the last byte, and it takes 50 milliseconds because of the speed of light doesn't travel faster than that over the Atlantic. You see the last byte, and you kind of close the file, and you are finished with the download. Do you understand? This is all latency for this operation. So we understand just the definition of the word. Latency numbers every programmer should know. Have you seen this picture? I'm not taking, by the way, any credit for this picture because other people have done it, but have you seen this picture before? Okay. This is very important when we are dealing with optimization because it gives us a small picture graphically of the difference. You will soon get, in my opinion, even better thing, but I'm just showing you. The important thing is this sentence here. You will be able to download this presentation from GitHub later with all the examples and such. So you will see this text, and there is actually a page with latency numbers every programmer should know. You can go to this page and you can move between years. And then you will see, because of course computers get better, right? So you can see what those numbers are for the current year, or how it was in the 90s, for instance. That's also interesting. Anyways, these are things, I won't go into specifics here. These are the things that are happening basically inside the CPU. Those are on this level, right? So operations are actually taking today in a single CPU core around like 8, 9 of them during 1 nanosecond. And 1 nanosecond is not 1 millionth of a second. It's 1 billionth of a second. It's so small that we cannot understand it with our minds. So we have to have some kind of tool to understand this. Anyways, if you have 100 of those things that are happening inside the CPU, then you have one memory access reference. So if you're going and just fetching a single byte from your RAM memory, it's actually 100 of those, just so we understand the scale. To continue, one of the most important here is what's happening on the SSDs. SSDs are very, very good, but to do a random seek, right, kind of, or it's a random read. Why it's written like this is actually because when you ask SSD, the least you will get is probably like 4 kilobytes or something, like a blob. But anyways, to do this operation, the minimum operation is, as you can see, first we have like 100 of those is one memory operation. Then one green one is 100 of those operations, and 15 of those are needed, like 1,500, like the blue would be like here, right? To describe how long it takes to just access the SSD one time. And then this is interesting also, we will see it soon. So to understand this in human understandable ways. Is this interesting, by the way? Because the first time I saw this was very interesting for me just to understand, because this is like vital to do optimization, right? So human understandable latencies, let's say that the things happening inside the CPU is one heartbeat. You know but the latency of the heartbeat, not like the pulse. So I'm just talking about how long it takes for the heartbeat to happen. That's around half a second in a normal human being. So for reference, and the CPU is all time spinning. Of course, it speeds up and slows down. I won't go into that right now. It doesn't matter. But if it's working, when it's working at max, so it's always doing something, doing some computations and such, right? So here you can do operations, and your programs can actually run here inside if you fit into the cache. Now, if you have to go to the RAM to work, it's comparable to this. It's like brushing your teeth. So it's all the time that I would actually go out there to the toilet where it is. You probably and pick up my toothbrush, put up the toothpaste, brush my teeth, and rinse and everything. This is one memory access. And let's see now. Okay, and reading 1 megabyte from memory is like 3 days. Almost 2 days for just doing this SSD access in comparable time, right? And then we have the absurdity, right? Okay, let's say, in the data center, let's say that you're pinging your brother's computer in your own home network, that is 6 days. And if you're doing a ping from the west coast of USA to Netherlands, or in this case, the other way around. No, it's actually from the west coast. 4 years, 10 months, almost 5 years in this time scale, where the heart is just beating, and it's just doing this thing all the time. Just to see the scale. So of course, okay, so the concept first, can we bring the data closer to the processing? So we will do an example by using the built-in cache. Can we in some way do something with the program so that it actually uses cache in some way? It doesn't matter. And how can we in that case do it? Maybe you have an idea. Exactly, yes. So we will try to, we will actually look at the program that uses cache. So, and this is actually happening, by the way, completely automatically. So it's not like you have to write the program in a certain way. It's just, as you will see, that it depends on how big the data that you are working on is. So let's see if I can find it. Oh, turns out that it wasn't prepared, but I will soon be prepared. I have to fire up the IDE.
So measure latency now.
Yes, exactly.
Is it WebStorm? Why it's taking so long?
Yeah, it's WebStorm. Some of you guys are already.
Your pain.
Yeah. Or it's actually PHP Storm, but yeah. Same problem, right? Okay. Oh, yeah. I think it's visible. So my first example is this one. And what we want to look at here is I have defined a few constants that represents sizes of arrays in memory. So we will be trying those sizes here. We are starting at 8 kilobytes, which is very little. It would be much on my first computer, which was a Commodore Plus 4, which had only 64 kilobytes at all, but as total. But then 1 megabyte, 4 megabytes, and 32 megabytes. We'll run this program and see, okay, what this program is actually doing. I will show you this. You can actually maybe see this here. What's happening here is that we are just taking this array, we are picking 2 points in it and swapping the values. And we are doing it a number of times. And the reason why we are trying to do random here is because processors are very smart today. So if we would do it like in a way where it goes sequentially, then it will figure out and read ahead. And we don't want to prevent this in this demo. So the actual examples will be here that we are doing the 32 megabyte, 4 megabyte, 1 megabyte, and 8 kilobyte. And you see that we are doing it's 10 million operations, spins in each of them. So let's see what happens. You can see the results down here. Okay, yeah, I will move this up. Sorry?
This can't be true. Doesn't make sense.
Well, it's 10 million times that's happening in each case, but the array is just different size. So still it's not like a big difference, but you see that there is a difference. Okay, you can say that there is a difference, right? Now, this computer is actually very old. This computer is from 2014. I would say, yes, 14. So it only had 3 megabytes of cache. So actually you can see this on this example. You can see this, that here you have 32 megabytes. I tried it on the server and it had the same speed as the ones below because the cache was huge. But anyway, so we have 4 seconds, or this is in milliseconds, right? So 4.3 seconds, 3 seconds, 2.5 seconds, and 1.3 seconds for the respective. You're seeing these sizes, right? So while it might be impractical to restructure your program so it's running in a small array of 8 kilobytes, for instance, it might be very impractical. It might be possible for you, for instance, to rewrite the program so it's working in a buffer of 1 megabyte, for instance. So one thing that you need to know if you're optimizing for this, by the way, it's if it's on a server, of course you are sharing the cache with other applications. So don't use, like if you have a CPU that has 15 megabytes of cache, don't use 15 or 16, sorry. Then usually you would optimize for a little bit less because you have to account for these collisions with other programs in the same computer. And always measure, measure, measure. I might be wrong. Maybe in your case it's actually like 17 is the optimal value to get the best speed, if it's very important. Yes, okay, so now we are...
It also depends on the kernel configuration and
Yes, yes.
pages.
So, absolutely. So the depth of the knowledge you can get here, and that's also point of the talk, is very, very... I'm trying to just scratch on the surface to start thinking in the right way. And then you can just Google and expand the knowledge to know more. So I'm going back here. Let's see if I... Okay, so yes, as we said, if this is slower and slower, this is faster and faster, and the demo was already done. The next concept, now we are talking about algorithms. I'm guessing that most of you already know what an algorithm is. Yeah. But, and I will take one of my favorite algorithms. Sorry? Yes, yes. I will actually show you the binary search because it's so easy, but it makes such a big difference. And then, of course, you can expand this knowledge to very impressive and really complex algorithms. But the binary search is like a game changer for many people once they see it for the first time. Anyways, is there anyone that hasn't seen binary search? Okay, great. So let's say like this. Okay, so you have a list. For binary search to work, you have to have it ordered. So that's one of the weaknesses of this algorithm. But anyways, let's say that we have a list, and as you see, it's not like we have all the values here. They are interspaced, the values. They are missing some integers, right? Anyway, so if the question is, okay, I want to see if this value, such and such, is in this list. So the normal thing, if you're doing it in a naive way, is of course to just going through the list and just comparing. Is it this? Is it this? Is it this? Is this? Until you either find it or you drop down through the list and you didn't find it. Very easy. Now the concept of the binary search, which is very simple. So simple that we can actually we can basically get 5-year-olds to understand it in 2 minutes, which is the beauty of it. I love it. The binary search is like this. So we are looking for a certain value, and in this case I actually made it easier for us to kind of focus our mind. So we are looking for the value 4 now. In binary search, what we are doing is, instead of starting from the beginning or from the end, we are starting at the exact middle. And we are saying, okay, so is this value, is this the same as the one that we are searching for? So now in this case, of course, it's not, right? But we can also say, is it more or less? Because we said that one of the requirements was that it's a sorted list. So we can say, no, it must be in the upper half then. If it's there at all, it must be in the upper half of this list. So we take the upper half of this list and get to the middle again. Okay? And now we are saying, okay, is 2 the same as 4? No, it isn't. Is it more or less? Okay, so it's more, the one we're looking for. So we are taking the bottom half of the list in this case, and we end up with this, and we go to the middle, and we found it, kind of. And to verify, yeah?
But in nice way, we have the same number of operations in this.
In this specific case, and you are right.
Worst case is what matters.
Exactly, exactly. So that's a very good observation. If we back up to this one, in this specific case, we have 1, 2, 3 operations, and the other one also took 3 operations to find. Now the optimal for this is when you are looking for 1, right? Then you have 1 operation. Now the worst case is if the number is not even present. We will be searching for 24 soon in this list. For this naive implementation, it would take how many operations? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or basically, we see that we have reached the end of the list. Okay, through this. Okay, looking for 24. Go to the middle. We must be in the bottom half if we find it at all. We are going to the, oops, lose focus somehow. Going to the middle again. It's still in the bottom half. And we're going to the middle. Okay, we can say not found, because since the highest value is higher than the one we're searching for, we can say it isn't there. We can actually even say on which position it would be, if it would be, right? So binary search. Now we should theoretically understand this. Basically, yeah, okay, I won't complicate this. We have demo 2 for this. And I have to move over this one again and go to demo 2. So what we described, what we were doing, is this code. I won't go through it because there are 1 billion or several million at least implementations on the internet, so you can look at it. But it's so easy code that you can actually follow it. It's exactly what we were doing, but we were seeing it graphically. So what we will be doing is, first we will create an array. This array is 1 million integers long. And then we are filling it with integer values, but random integer values. So 1 million random integer values. That means, of course, that there can be missing values, but there can also be duplicate values, for instance. And then array sort, because this is a requirement for the binary search to work at all. So this is the initialization of the test data. Then we have the, see here, yes, this is the naive implementation. I'm using here, okay, so you see what we are doing. We are going through 10,000 searches in this 1 million integer array, 10,000 times. We are just picking some random search value between 1 and 1 million, and then we are searching for it in this array search value. And then if we have a hit, we just count it up, so we see that something is happening in the program. And of course, as you can see, we are measuring the performance. Oh, I forgot to tell you, I'm using this built-in thing to measure performance, by the way. It's called perf hooks. This is built in Node.js, so you don't have to install anything to have this available. And you, as I said before, can use the code. Oh, by the way, if you don't program, yeah?
Just a bit curious, actually sorting is expensive. And what Node.js uses for sorting and what kind of algorithm do you use? Like, yeah, it's under the package, but still.
Yeah. I'm not sure right now. We can Google it, and it's very easy, and it's outside the scope of the talk. But we can talk about it later, absolutely. Yeah. Anyways, okay. Index of. Okay, so just if how familiar you are with JavaScript, but index of is talking about. Loop here, if you want, go through the million values. Index of is doing the same thing. Yeah, and then we have the other. I see that my ASCII art completely fell to pieces here, so it's not even fun. But so we have the binary search, and instead of doing index of, you are seeing that we are using the binary search. We are sending in the array, and we are searching for the search value. But again, 10,000 times, and the same, search value. So let's run this program and see if it makes any difference. Did it make any difference? We see that here we have the initialization. Then we have look up random value 10,000 times using array index of. It took a little bit over 6 seconds and found 6,229 hits. This was because not all values are present, right? As we said. And then we had another run, but then we were using the binary search, and we are down to 24 on this slow computer. 24 milliseconds. For the exact same operation, you have the exact same,
What was the hits?
The hits were that since I was initializing the 1 megabyte array with random values between 1 and 1 million, you would get some duplicates, and therefore some of the values would be missing. So the hit is when it just took one random value and it found it. So, okay, this was this example, and this was about algorithms. So, the way of thinking, we're going back to this question that we had in the beginning that I said was probably the most important question is, what am I asking the computer to do? And the key line, of course, in this kind of simple program, but still, you can break down your problem to be this simple as also. And you see that we have a cheetah and we have a turtle. And the turtle is not that bad. If you think about it, we had 6 seconds for 10,000 lookups. So it's actually going in less than 1 millisecond. So when you're first writing the program, you won't even see this. You might be writing a web service, and first when you have lots of hits, you will see that it actually takes kind of much time. So, okay, the cheetah represents when the size of the data is almost, not completely, but almost doesn't matter for the speed of the operation. It's because, okay, in fancy talk in computing, this is called like time complexity. But we won't touch this. You can Google it and you can learn it, but this is like a course. But to get just the understanding and start using this, you don't need the course. You can start with this, and then you can learn more. So the cheetah is when the size of the data makes almost no change. I could have a terabyte if I had the RAM, and you would not see the difference here. Yeah?
What if we send these values to the hash map and we will search this faster?
We come to the hash map, and that's the part of the structures that we have in JavaScript so that we can use them automatically. But we come there, absolutely. So okay, a turtle is not that it's slow per se, it's that it gets slower if you're adding more data. Probably this would be 2 times slower if we added double the data, right? Because of the way it works.
I would like to add something. There is a very interesting case when it comes to parser performers.
Mm-hmm.
And this is about parsing remaining arguments in
Mm-hmm.
functions.
Yeah.
So this is like related. I see it as related argument. This is what you said, that you need to make decisions based on your input data, input size, or range of input, because sometimes I've seen this multiple times in like source codes of some popular libraries.
Mm-hmm.
You just inline. So let's say you have to parse multiple arguments in your function.
Mm-hmm.
Sometimes it's easier to inline inline 4 arguments
Mhm.
in your code, because then parser is going to, like cache compiled byte code,
Mhm.
and it's going to be executed faster. And this is like proving example for this, what you said, that you shouldn't be doing like, array processing if you need multiple arguments. Sometimes you need to inline arguments and make it execute faster.
Mhm. Mhm.
I hope you understood.
I understood, I think, but I might be on a level that
Yes.
maybe the whole audience might not understand.
Yes, it's
But-
like,
Yeah, yeah. And also a good point of like a sidestep from what you were saying, that's why we are measuring, but because sometimes, as we said before, if we would be reading data very sequentially, then the CPU is so smart that it will like see what you are doing and do things faster, so you might not need to optimize in this case, just so you know. That's why we are measuring. Okay, so the concept tree was what I was mentioning before. So if one task is taking 1 millisecond, then 1,000 tasks take 1 millisecond is 1,000th of a second. So 1,000 millisecond tasks take 1 second. And that means, so we understand, because you are Node.js programmers, at least some of you, if you are writing a web service, if you have something that takes only 1 millisecond, which normally is counted as a very fast response time, if this is CPU time, this request, if 1,000 users hit this request at the same point, they will get on average response time half a second. Just, it's worth to think about, because these things multiply. Also part of the optimization. Now we are going to JavaScript data structures. And I found this picture today on the old drive. So I'm very, very happy. Do you know who this guy is? This guy is Douglas Crockford. He is the guy that invented JSON. He's the one that, like, wrote it out first on a napkin or something and invented it together with his friend. Anyways, he writes extremely good JavaScript books. One of the best books in the, actually not JavaScript, it's one of the best programming books I have read in my life is JavaScript, the good parts. Because JavaScript is like some would say it's a sloppy language, but he shows how you can use it like a powerful language to do like anything you want.
Have you read You Don't Know JS?
No,
Okay,
haven't.
Because I wanted to ask, how do you compare those two books? Because I've only read You Don't Know JS, and I'm interested in alternatives that I can learn something new.
Okay, I haven't read the other book.
Okay, but
Yeah.
you recommend books from this guy?
From this guy, especially the first book, which was JavaScript, the good parts, because he has a good JavaScript, the bad parts, right? Also, as another book. Anyways, so we are talking about JavaScript data structures, and we are talking about lists and objects. These were the original data structures that were built into JavaScript from the beginning. Now JavaScript is a competent language, has like maps, real maps, and has like other stuff that you can use. But the reason why I will focus on this is because of time constraint, of course, because we cannot learn everything today, but also because those two work together with JSON. Like a map in JavaScript doesn't have a representation in serialization. So that's why we're doing that. And we can actually do extremely much with just those two. I have probably not yet to see some limitation that you cannot implement if you have those two. Okay, so JavaScript list. Are you, by the way, programming in JavaScript regularly, or TypeScript, or JavaScript? Okay, yeah. So many of you, this is basic for you, of course. A JavaScript list is like this object which takes 0 or more items. It's ordered, so you can always talk, and it always starts from 0. So the first item is always 0 if it's there, and then it goes up 1, 2, 3, 4, 5. You can access the items very fast by index, and that's the strength of it. And the items can be like, it can be strings, numbers, or others like the primitive things, but it can also be another list or another object, which we will soon come to. So I actually think that the graphical representation in JSON is very, very simple to understand. I don't know. Okay, let's try it on this on you guys. So this is the empty list, right? You don't see any item in it. Then you see 3 numbers in this list, and it's represented with just this comma between the items. You see that we can also have strings in it, and you see that we can even mix different primitive types. The last one is a little bit important though. Is there anyone that has a problem with seeing what the last list here, down here, is? Do you see it, by the way?
Yeah.
Yeah. So this list, these are actually two lists. The outer list has 4 items. So the first item is an A. The second item, and this is important, is a whole other list, which ends at this comma. So this is on the outer list, this is a whole item. Then we have a number which is 15 and then a string. Now in the inner list, we have 2 items. The inner list starts here. It has this string, and ends here. This is a complete own list, but it's also the second item in the outer list. Is this clear? Yeah. So the characteristics, again, this is time complexity, but explained in easy terms. Okay, again, so just to understand, it's not that the turtle is very, very slow. It's just that the turtle gets much slower the more data you add. That's the point here. Okay, so when you're searching for item by the value of the item, then it's slow. If you're adding the item, it's slow if you're thinking that you're adding the item wherever in the list. But there is a special thing, a special case in the list. It's when you are adding to the end of the list. Then it's the cheetah again. Then it's fast. So that's okay to do if you are dealing with, optimization. Then delete item is almost the same as add because of the same reasons. But accessing the item, and I forgot to write by index here, is the cheetah. That's the point with the list. You have the order, and you can access all the items by their index, their inherent order.
Is it push comparable with unshift? So you have the element to the first.
Absolutely. What is the operation? Because here we have push and pull, right? What is it called to do this in the beginning?
Unshift.
It's, yeah, this is slow. Yeah, or might be slow, actually.
It's all because of how actual memory
Yeah.
physically works in the computer.
You might have to move the whole list into a new,
So
yeah.
If you want to put something in the middle, you have to
push the rest.
basically push the other half forward.
Yeah.
So dependency on the implementation, one another sheet. Dependency on the implementation, because if you would stick to the list, which is in the header of the slide, then actually you can speed up adding to the beginning of the list by reversing the list and then appending it at the end and then reversing once again. But it depends on the implementation. So
again, and here you see someone that has been programming a little bit. This is the way that you can start thinking after a while, right? If I'm doing like 1 million operations, then I can actually use this to my advantage, as you said, right? If you reverse the list, if the point would be from which way you are doing this. So very smart, very good point.
It wouldn't scale for a small amount of items. For small people.
The thing that costs is the reverse, right? Yeah.
I mean, talking about the overhead. Or pushing.
Do a test program, guys, and measure it.
we can have a programmer's fight.
Yeah.
Yeah, 3 to 1.
Yeah, we are at the JavaScript object, which you in JavaScript write. Okay, by the way, the lists and arrays is an interchangeable phrase. By the way, I'm sorry, because I forgot to tell you, but so if you hear array, you hear list in JavaScript, it's the same thing. The JavaScript object, though, is something that was built into JavaScript. It's when you're writing it in JavaScript or initiating an object, you usually do it as a literal, which is those, what is it called? Braces, exactly. That was what I know. These are done with these braces. To describe the object for a new programmer, I would say it's a little bit like this dictionary. So if you have, let's say, the word owl, you know the owl, the bird. So you would each entry in the dictionary has a key and a value, and the key is the word you're looking for, like owl, and then you have the description of the bird, like the night bird, hunting, big eyes, or whatever. That would be the value, and the name is the owl. The thing is with the objects that you can have very many of those key values, and you can search for the key very fast. So that's the advantage of this data structure. So in JavaScript, keys can be a number or a string. You cannot use in this object, sadly, like object or something else as the key, but you can use maps for that. This is just the side information. There is an object inside JavaScript called maps where you can do this. But this, as I said, has the advantage of working with JSON. Keys are unique. That means that if I wrote something in the value of owl, and then you come and you are writing another description and putting it in the owl, then my is replaced. It's not like you get 2 owls. Then values can be primitives, or they can be other list and objects, so you can have complex values, and access by key, as I said, is very fast. Very instantaneous to find the owl or find the eagle or whatever. JavaScript object examples is the empty object. Then we have the object that is describing some properties of a person, for instance, which might be the name and height. As you can see, this might be used if you have a long list of people. Exactly, you can have a list of people where each item is an object. And then, of course, the names and the heights would probably change of those people. And to see a more complex thing you can do with object is that, yeah, you got the joke already. Yeah, I saw that. Yeah. Do you see the joke? Do you see it? Yes. You can have, for instance, kinds. You can say bird, bear, and dog, and then you have the different, specific races or whatever you would say of this creature. And here you see that the key is the kind or whatever you call it, and then you have a list of the specific instances or races, whatever it's called. Is this clear, by the way? Is someone that is wondering about this? This is an object that has strings for keys and lists for values. Yeah. So JavaScript object characteristics. Here we have a full cheetah. And then I want to hear an intelligent question.
Where's turtle?
No, yeah, of course. And why would we even use the list at all, right? Because if everything is fast here, why bother? What? Order. Yes, exactly. And that's the answer there. The list has the order, and the dictionary doesn't really have it. You can search for keys, but you cannot never tell which key was inserted before another unless you keep track of it yourself. So. And then we will have the practice. We are soon finished, by the way. It took us some time, but I want to show you that you can do something with real data on this. So, airport database. This is open data, so you can that you can find on this URL here. It's down there, but as I said, it will be on GitHub, so you can download the presentation and copy paste it. It's open data, so you download like a CSV file, which I did. I converted it to a JSON file, and I converted it to this file where it is, as we'll see soon. It's a JSON file, which is a list of lots and lots and lots of objects, where each object is this airport and data about it. So we will do first the unoptimized version. Okay, we are looking up results by iteration. This one, and to tell you a little bit about the setup here. First, I'm reading the whole data, and it's like 70-something thousand airports. Some of them are, by the way, like just a helipad on top of some building or something. So it's not like airports, but it's places where aircraft can land. And so we are reading all of this data into memory. We'll be using it for testing. And we are writing out how many of those there are. Then I'm doing a filter. This is not part of the speed test per se. I'm just filtering the ones that have an EATA code. Do you know what an IATA code is? This is when you are flying to Warsaw, then you have WAW, that's the code of the name. When you have the boarding pass, you know from where to where. You're flying to London Heathrow, it's LHR, right? London Heathrow. So this is the IATA code in their language, the people that are working with flight. So I'm doing, there are lots of airports that are small enough, like the helipads and such, that don't have an own code. So we are like filtering out those, and we will be searching for the airports that we can find by this code. And what I did here, and this will be in all there are 3 examples, and then we are finished. So first we have the naive example, which is looking up, as you can see. I'm not doing index of because it's harder to do here. I just do a normal loop through the list of all the airports, and I'm looking for the IATA code that we are searching for. So this is the naive test version of the lookup function. Then we have a driver function that is just for the testing. It's actually going through all the airports that has an IATA code to see how fast it can look them up. And then it adds a fake IATA code. And the reason is that we want to know that our function is working properly, that it actually says that there is no hit on this. So this is just a driver. This will be the same for each of the examples. The other one will be, of course, changed because we will see the optimized way of searching. Again, we are looking the time it takes to do this. And in this case, of course, it's all the airports with IATA codes that are the kind of the ones we're testing. And so let's run this one. Oops. Start running. You see that the initialization went fast, right? We have 71,600 airports, something like that. And then we had 9,250 airports that had the IATA code. And now it's finished. It took, on this computer, it took 10 seconds to go through the whole list of all airports that has an IATA code and look them up in this big list of all the airports that we have in the world, basically. And find this airport and just get all the data about it. 10 seconds. So now you will have to remember this value. 10 is kind of easy to remember. Then we will do another strategy here. Now we are talking about optimization using the things we have built into JavaScript. So the next thing, and this is actually a word, so you can search for memoization. This is what we will be doing. This is an optimization strategy where you are looking up the result, but once you look up this result, you're storing it in some kind of a cache or something, some side storage, so that if someone asks for exactly this thing again, you don't have to do the very hard task of looking it up. You actually just answer the same thing back. Kind of easy, right? So yeah, let's go to the code at once. So the function that is doing this by memoization, this is the only thing that has changed from the other program, by the way. It is just this function, how we are doing the lookup. What we are doing here is that we have a memoization store now. We are creating an object that from the beginning is completely empty, of course. And then when we are coming in here and asking for an IATA code, we first check, do we already in this cache or this memoization store, do we already have a result for this? Because then we can just return that. We don't have to do all this tedious work. Of course, the first time we come in here, it's empty, so it will have to do the work, right? Then we are going through all the airports, and then we are returning the airport that we find, just that if we find it, we also put it into the memoization store. As you can see, this is the object, this is the key, and we are just setting it with the airport data. So it's there the next time around. Yes, and let's see if this makes any difference. Now, by the way, of course, I'm running it 2 times because this is memoization. So let's see what happens. Yeah. Again, this took almost 10 seconds. Not that strange because it's the same thing we are doing.
But still faster.
What?
But still faster.
but still faster. So this is probably a difference of other things that are happening on the computer or something. It's very, very similar timing. So you see the difference here. And of course, this is like the unoptimal case for memoization, because this is when we don't know anything of the ones we are searching first, and then we are searching for all the ones again. So first we see all the advantage coming in the next run. But you see the difference here. You see that the difference is kind of much, right? This is 27, so 9,000, 10,000, 10,000 through 30.
A lot.
Yeah, a lot. It's like several hundred times, right, of difference here. And this is because, as you can see, as I promised you, I said before, this one is searching very fast. As long as you're talking about the key, it just happens at once. It's actually it's using in the background. It's using something that is slightly better, I would say, than a binary search. But that one is like the next course that you will have to read about yourself. No, it's hash buckets in the background. Yeah, yeah. So, and we will do the last thing, and then we can do other things. Lazy pre-calculation. So what is this? Okay, so on the first lookup, we build the pre-calculated data. And then on subsequent lookups, of course, we are returning the pre-calculated value. So that means that when, yeah?
If I may add something.
Yeah.
So in Java, not JavaScript, but in Java,
Mm-hmm.
there's a very interesting case with the order of keys in hash map.
Yep.
And recently, like standardization committee, they tried to put it into standardization.
Mm-hmm.
What's the order of keys?
Bad idea.
You know, but you know about this case?
No, but bad idea, I was just saying.
Yes, so, and it turned out, that some software manufacturers were relying on the order of those buckets that much
Yep.
that they were complaining on putting this, like, so this implementation details of those buckets.
Yep.
But generally, they finally stuck with the, I think, initial implementation.
Okay.
But it would be faster. But this is like it's like sometimes standard is saying that the order of those buckets might be something, but generally you don't say that because this might be improved in the future.
Exactly.
There are like higher caches and so on. So yeah.
Absolutely. In Python, to circumvent this problem, they actually, at some point, it was also that people were relying on the inherent order of these hash maps. So they did it random, specially, just to make people stop using it this way. Yeah. Okay, so pre-calculation, again, last example, and then you will basically be free. Yeah. So the last example is, we are looking again at the lookup function, which is the important one here. How is it doing stuff? So let's see. Yeah, I hope you see all the code. We start with this store as we had before, but we don't even initialize it. So it's null. From the beginning, there is no store. And what happens is that we come in here and we are looking for a code. If there is a store, then we are presuming that it's all pre-calculated. So we just take the value and we return. This will be as fast as when it was fully memoized in the previous example. What we are doing if we don't find it though, is that we create the pre-calc store in this case. We are going through the whole list of all airports. We are putting it so that the pre-calc store is populated. And then we are, in this case, actually, we are doing a recursive call to get it from the store, but we could just get it from the pre-calc store at this point. I wrote it too complicated, actually, than it needed to be. But anyways, so we will see now how this works. So now the program ends almost at once. The initialization is fast, as you saw, and now we have almost the same values on the first run and the second run, because it's only when we are looking for the first value the first time that we are pre-calculating everything. So again, there is a question here. Why aren't we doing this on all data? So if pre-calculation, lazy pre-calculation is so awesome, why aren't we doing it everywhere? Yeah, exactly. So if you have, several gigabytes, it would be so impractical for the first time someone is asking for this value that it takes for him 5 minutes to load it up, right?
Or you have to fill serious time.
Exactly. So you are already... Exactly. So you're already thinking the next step. My point again is here, we have to measure, because the thing that we find is intuitive might not be the truth. So, okay, to round it up.
Could you run it a few more times?
Yeah, of course.
Because now the second run, I'm wondering whether we'll have it in such a way that first will be longer. And no, I would like to see whether is there any case that second call will be
longer than the first.
Because this would mean that your cache in your virtual machine in JavaScript is not working.
So all of these things, when you are doing those tests that are going so fast, they are very reliant on whatever is happening on the computer. So we would.
Yes, I know, but it's like I'm just curious where will we be able to achieve it? Like
36. Yeah.
So
43, 20.
Generally, it's always faster.
Yeah. It will probably happen at some point. Yeah. There it was. Yeah.
But generally, it's because there could have been something like in the middle happening on your operating system, but generally, thank you.
Yeah. Okay, so this was the last example, and so yeah. Okay, back to the presentation and just the ending of all. So the summary. The most important question, I would say, is to say this question: what am I asking the computer to do? Because I see that many programmers, this is actually one of those things that are coming with the experience. Many programmers are just writing something that they have done so many times, but they are not reflecting. It's more like they using this. As we said from the beginning, right? The cargo cult programming. I always do this way. Start to think about what's happening. Then measure. Even if you think you know, because this is one of the biggest traps as well. Even if you think you know where the time is used, it's so stupid if you, for instance, have optimized the processing that takes 1 second, so it takes like 100 of a second, but actually the writing of the data then takes 10 seconds, then you just feel stupid, right? You have lost lots of time. And learn more about algorithms and data structures. So this was a primer. You saw how much you can do if you just know a little bit. So it's not like you have to do this big step. Start with the small ones, but then you will see there are like trees, there are like lots of sorts and other cool stuff. So when you look at this, and that's also the point, some companies, when they are trying to hire you, they are trying, to see how much of this you know, but they are doing it often, I think, in a very stupid way. Because you're putting stress on people and you're not really seeing how people are doing in a real life situation. But okay, that's another chapter of this. But anyways, learn about algorithm and data structures. That's it.